All right, welcome back to another exciting episode of CS250B. Up until the last lecture, we have been talking mostly about the performance engineering of software systems, performance engineering of software. And we've been looking at it mainly from the lens of improving memory access, which was a good place to start because at least anecdotally, most of the performance problems that I've and many other people run into when they are just naively writing software are memory access issues, caching issues, eviction issues, things like that. But provided that we manage to stamp out a lot of these memory-related performance issues, including caching issues, using cache oblivious algorithms, instruction cache issues, things like that. Once we get rid of the main memory issues, then the performance bottleneck moves to computation, provided that the memory can ship the data over into the processing unit as fast as the processing unit can process it, then the performance of the memory is being bottlenecked by the computation. The question here becomes, can the computation unit do better with the off-the-shelf processors that we already have ready on our desks or in servers? And before we actually go into that topic, and if I could, I would like to go over the 40-ish slides that I've prepared for today to get to the punchline at the end, but we'll see how much we can do. But before we get into the actual programming methods and things like that, I'd like to spend a little bit of time talking about Perftools and how to do performance profiling of software with them on Linux. So performance profiling with Perftools. So yes, how do we evaluate the engineering approaches that we've made so far? Say we made a performance engineering change in our program, we tried to do something better with caches or something else, and despite our best efforts, performance decreased by 10%. It takes 2 seconds longer than before to finish the program. The question then becomes, why did this happen? Can we know why? How do we get rid of this problem? And that's where profiling comes in. Profiling, And there are many tools available that provide profiling capabilities, and these do become absolutely necessary tools when you want to do performance, or even, among other things like correctness. But if you want to do performance aware of development, some of these tools will become absolutely necessary. And there's a lot of tools, gprof, which is part of the GDB toolset, oprofile, Valgrind, FreeTunePin. There's a lot of these things. But today, since we're going to look at one of the simpler options, we're going to talk about Perf, which is part of the Linux Perftools. The reason we'll be talking about Perf is that it's a canonical part of the Linux distributions. It has native support in the Linux kernel. There are syscalls and a lot of support infrastructure in the Linux kernel itself, which were put in to support Perftools in particular. So they do a very good job of doing, and low overhead, very good job of doing things on Linux. And the tool itself is very simple to use. Of course, it also has a lot of strength if you get into the weeds of it. But from a beginner's perspective, when you first start doing performance profiling, this is a very low overhead tool to get into. And on top of that, it has a very straightforward PMC support, performance monitoring counter support, and let's see what those are. So on a side, performance monitoring counters, or PMCs. They're here on their architectural entities on our processors to solve the problem of how can we measure architectural or track architectural events. Events like how many L1 cache misses, how many branch mispredicts, how many branches in total or something, total cycle count that we took to execute this program or a function or a method. How many instructions have we executed as part of this function or this program or process, et cetera, et cetera. And these are architectural features. So there's really no way for the software to know to know at least in detail and fine granularity when and how these things are happening. Partially because architecturally, these are not exposed to the software because these changes are supposed to happen transparently from the software that's running on them. And also partially because these events happen too often, too fast. So even if there was a way for some interrupt handler or something to be called for a user-defined software to keep track of them using an array or a register or something, there's really it's too fast for the software to be handling them at any reasonable performance. So PMCs, performance counters, are the solution to this problem. These are also sometimes called hardware performance counters, so performance counters, depending on which document you're looking at. So PMCs or PCs or HPCs. And PMCs are dozens, typically in the orders of dozens of special registers that exist on modern processors, even on modern processors, even on our smartphones and whatnot, on our modern processors that can be programmed to count such an architectural event. We can set a mask on one of these registers to increment itself whenever, say, branch mispredict happen, for example, or a cycle increases, things like that. These are privileged registers, meaning they can only be accessed by the kernel when they're running in supervisor mode. So if a user thread or user process tries to run the assembly code to try to access these registers, it will cause a protection fault, access fault. And of course, these are, I guess they're not obvious, but supported PMCs do differ across processor models and designs. Pentium 4 has like 12 of these things, supporting such and such sets of sampling sources. Core 7s have different sources, ARMs have different things depending on their models. The PMCs that are available on my i5 desktop will be drastically different from the PMCs that are available, if any, on a Arduino board. Well, Arduino board as well. I don't know if they have any on a Raspberry Pi board. And the typical low-level usage of PMCs would be, we can program a PMC to keep track of some particular event. We can read the PMC to get a value before we run the original value before we run a piece of code. A piece of code could be a whole program or a function or whatever. And then we run the code, and after we finish running the code, we read the PMC, and then we compare the read values to know things like how many cycles have elapsed over the duration of this code execution, how many L1 branch misses, L1 cache misses that we have to suffer during the course of this execution, how many page table walks that we did, things like that. Well, page table walks are not counted by PMCs, but things that are counted by PMCs. So Perf lets us use all these features in a very simple way. Like mentioned before, Perf is a performance analysis tool in Linux. It's natively supported by the kernel, and it supports profiling a very, very wide range of events, spanning from things like reading from the PMCs to software events that the kernel keeps track of. And it has many operation modes, many ways you can execute it, including commands like top, stat, record, report, things like that. We'll get into some of these in a bit. And you can check out the list of the supported events found by running sudo, because it needs to run in kernel mode, sudo perf list. And on the left, you see a list that is maintained by the hardware performance counters, things like how many branch instructions, how many branch misses, how many bus cycles, cache misses, cache references, things like this. A lot of these events have some caveats and strange details about what exactly do they mean. So once you start getting into the weeds of how to actually run or parse these the results, it does sometimes get a little bit involved in terms of architecture, but at a high level ballpark, back at the envelope level, these are very straightforward result that the tool will give you. And a bunch of stuff are omitted here because this list is very, very long, but it also includes things like one cache misses, D cache misses, last level cache misses, things like that. And also keeps track of software events that happens in the kernel, things like page faults and also things like that. There's a lot of events that you can keep track of. The simplest way of using perf when you're running a short snippet, a short program, would be to use a perf function called stat. So if I want to know the performance details of the ls command, for example, I can run sudo perf stat ls. This is the default command which prints some useful information. Here you see the default events that the tool keeps track of, including how much time it took for the program to execute, context switches, CPU migrations, if any, how many page faults, and just running ls seemed to have suffered quite a few page faults. How many cycles in the CPU, how many instructions that it executed, branch misses, things like that. An interesting thing here is just since we have these numbers in front of us, the number of cycles that it took to execute how many number of instructions, these two numbers are pretty similar. So we can see that there's not a lot of, hazards or branch issues. I mean, you can see that there are not many branch misses, so on and so on. So this is pretty useful. This can be very useful when you try to profile your code. If you want to trace more events, if you want to keep track of more events that you can find in the list command, you can add them using the -e command argument. Sudo perf stat -e. You can do all the usual stuff: tax clock, page faults, etc., etc. I tried adding LLC loads and then the LLC load misses when running ls, and now we can see that the last level cache load requests is 9,000-ish, which is actually not, it's a small program. It's a short program execution, so the number isn't very high, and you can see how many misses of that we actually have to suffer. And these kind of numbers kind of guide you how your program is doing. And this works perfectly fine when your program is kind of homogeneous, like if you're running a benchmark that repeats the same thing for a long time, for example. But it can get a little bit too high level when you're dealing with a piece of program that has, say, execution phases internally, when there are two different things that you do in the program, and you know that one of them is fine, but you don't know how the other is being affected. And that kind of a more complex scenario, you can use the record and report functionality. You can log events to a file using the stat perf record command. And then once that finishes, the program execution finishes, you can use the perf report command to interactively analyze the collected information. So you can do things like sudo perf record, you can give the e argument for all the stuff that you want to keep track of, and then run the command that you want. And this will generate a file called perf.data in your local directory. And then if you run sudo perf report, it reads the perf.data file and you can use your arrow keys and whatnot to navigate the tool to look at what exactly is going on. For example, I tried running the tail command, which reads the last n number of lines from a file, from a relatively big file. And when it finishes executing and I run perf report, the screen shows me this. There were 8 samples it took in terms of cycles, instructions, 1 cache loads and misses. And if I look at the cycles, if I press enter at the cycles while highlighting the cycles part, it shows me a list of the functions and how many of the cycles are being spent where. For example, here it looks like 96% of the cycles are being spent inside the tail command, inside the tail binary, which is expected, of course, because that's what we're running. But most of them are being spent inside memcopy. And you can actually move your cursor to memcopy and press enter to see which assembly instruction which are that are actually being the time is mostly spent being spent in, etc., etc. But at a high level, at least, we can know that this top function, this memcopy thing, is where the most of the cycles are being spent. Yeah, and if, for example, if I went to dcache load misses and print enter, I can see a similar output. And here also, you can see that most of the L1 cache misses are in a function inside tail called copy page. Of course, these symbols don't mean too much to us right now because we aren't the people who wrote the tail command. But if we were using this tool to look at our own program, then all of these could be very illuminating. A good thing about using this kind of tools to profile, so there are multiple different paradigms in profiling software execution. One is these this kind of performance counters based methods. There are other ways where you can instrument the code with some debug management code, or there are other tools which also moves the entire software into a sandbox so that you can execute, you can control things, fine-grain things like clocks and everything. In all of these paradigms, this kind of dynamic methods, including things like perf, are sometimes desirable because they're very, very low overhead. So overhead in typically, of course, your mileage may vary depending on what you do, but the overhead is typically inside lower single-digit percentages. So there was a question about performance. I hope that answered the question. And also another question. Cache misses. Yeah, approximately 36,000 cache misses. That seems to be the case. It's a very short program. Yeah, so this has been perf, high-level introduction into perf. And hopefully, I think this will be pretty important when you actually start doing lab 1. And of course, in the whatever future software projects that you run into, but most importantly, most immediate importance is that I'll be using screenshots of perf to show some of the improvements that are being made. So hopefully that will be useful.